This is the last talk of the day. That's always fun. Okay, so this is not going to be too deep a talk, but I think this is a very important talk because this is about the shape of what you'll be seeing in the future. Let's see what's going on. Okay, so this is a graph from a paper I had a long time ago about how to do parallel learning. And I don't really want you to understand the graph, I want you to understand the axis there, which is the area under the precision recall curve. So this is one of those things where you're trying to predict something like which ad is someone going to click on, and now you're evaluating something called area under the precision recall curve, which is some metric you make up that's kind of related to whether or not somebody clicks on something, but it's not very related to it. And in some sense, I think this talk is about something that non-machine learning people assumed was happening, but was not actually happening. The actual situation for how people were trying to create better models for how to personalize looked a lot more like blind people trying to feel it out than you realize. And the reason, what was really going on was people would try to go from correlation, assume that's causation, and then they would go and they'd deploy an A/B test to check and see if that was actually true in practice. And oftentimes it kind of was, and so people became better and better at that. But and systems became better and better at actually getting at what is the most interesting news story or most interesting ad or whatever. But the situation was really like this. It was people who were blind. They were looking at correlations in their data. They were hoping that those were causation, and then they would do an A/B test. And this is just the standard way that people did things, and they still do things in large internet companies. Okay, so I'm going to talk about a different way of doing things. Fundamentally, this is using the same kind of mathematics which goes on inside of an A/B test, but turns out that there's a way to directly learn at causation. And because you can directly learn at causation, you can instead of having area under the precision recall curve, you can draw graphs which talk about, you know, your click lift, or you're increasing your reward function, or maybe something about what was Susan's term? It was for people who sit around too long. Yeah, so you could have that on the y-axis, right? You could say, if you use this policy, people will not sit around as much. Okay, so an infovore is an information-based life form. Think about carnivore, except now we're doing information. So I'm going to talk about a system which is an infovore. It's something which creates data, and it consumes the data, and it uses it. So we want a system that can kind of sense the world, that can act and observe the outcome. Okay, and then your goal, of course, is to act in a better fashion. Okay, so an example of this, which is very relevant to Microsoft, is which news article do people want to click on, right? There are many other examples at many other companies, and in fact, this is I'm from Microsoft slide. There's many other examples inside of Microsoft, all of which have problems of the sort where you really want to get at what is the causally correct thing to do in some situation. You only really get feedback about the action that you actually take. And then the question is, how do you do that? And the claim is that you really need to be playing around with exploration on top of the standard supervised learning paradigm. So when you go out and you look at what's going on with respect to machine learning in the world, the standard thing is in fact supervised learning, where people have labeled information like ImageNet or some of the speech recognition data sets. People are making great progress there. That's fantastic. But there's a lot of other problems which are at or just beyond the frontier of machine learning, where you want to be getting at this kind of information where you only learn about the outcome of an action that you take, and then you're all of a sudden forced to think about causality and how to do exploration and things like that. Okay, so the setting that we're going to be talking about is Contextual Bandits. Contextual Bandits, so why is Contextual Bandits an interesting name? let's just go through what it is first. So you see some features, you choose some action, and then you observe some reward for that action. So this is the simplest possible infovore that you could imagine. It just gets immediate feedback about the action that it took. And now, compared to supervised learning, this is harder, because in supervised learning, you kind of know how good each of the actions you didn't take are as well. That's kind of the key difference between this and supervised learning. But this is actually simpler than reinforcement learning, which people have heard about reinforcement learning, I assume. Even many people not in machine learning. All right, so there's a lot of fun stuff going on in reinforcement learning, like solve and go and playing video games for you. It's kind of fun because you could come home and like the computer could say, I had 3 units of fun for you. Anyways, what contextual bandits are is a subset of reinforcement learning that is always tractable, in the same sense that supervised learning is tractable. So when people say contextual bandits, they mean a kind of reinforcement learning which is always tractable, or which is consistently tractable in the same way that supervised learning is tractable. That's kind of the key reason why it's a good idea to think about contextual bandits. If you can frame your problem in a contextual bandit setting, then you can solve it consistently. If you cannot, then you're on an adventure, right? Okay, so the history of contextual bandits actually starts over 20 years ago. This is a fantastic paper where they didn't call it contextual bandits, but they essentially proposed the first algorithm for this. Interesting. I'm going to make that go away. Here we go. Okay. There have been a number of papers which has talked about how to take the information that you gather when you're doing exploration and use that to train supervised learning algorithms. We actually have a library of different techniques for taking this causal data, which consists of here's the features, here's the action, here's the reward, and oh, by the way, here's the probability that I took the action because I was randomizing. We can take that quad of information, and we have several ways to boil that down into the kind of here's the features and here's the label that a supervised learning algorithm wants. Right? And they've gotten progressively better over time. That paper was actually the one where we first named contextual bandits. So I think there was a claim that the last person to discover something has the name stick, like Columbus, right? Anyways, people have obviously studied this kind of problem in the past, but nailing down this sub-problem as something which is kind of consistently tractable, I think is pretty valuable in terms of, well, Susan was talking about contextual bandits because this is tractable, and she doesn't have very much sample complexity. Okay, so we've been thinking about how to achieve both computational and statistical optimality. The first algorithm was computationally horrific. It's something which you would never consider actually running in practice because it's kind of exponentially slower than what we would normally consider a learning algorithm. So we've been thinking about how to make it computationally tractable. Oops, I think that one's supposed to be a 14. And then we've been thinking about how to do non-stationary policy evaluation. So if you have a stream of data being spat out by a contextual bandit learning algorithm, you might ask, what would happen if I used a different exploration strategy? Or what would have happened if I'd used a different exploration strategy? So it turns out you can do that to some extent. We have some techniques for doing that, and they've gotten better. And then this is really about making something deployable. And I want to kind of emphasize that this is a big step. So let's see if I can do this properly. All right. No, it's not going to let me. Okay. All right, so algorithms for learning from contextual bandits are in a piece of software called Deployable that I've been working on. It's open source software. It's widely available. It's widely used. But because we're talking about an infovore, something which needs to gather information and consume it, you need more infrastructure than just the learning algorithm itself. You need something which helps you gather the information, which helps you do the exploration, which joins the outcome to the event itself. And that's really what the subject of this talk is about. Okay, so exploration is something that I expect most people understand pretty well because people are used to it from clinical trials. There's a key observation, though, which is when you're doing a clinical trial, you have some policies you have to propose in advance. So Susan was talking about the particulars of how she specified the policy they're going to use. When you're doing contextual bandit learning in an online fashion, that's not exactly what's going on. So what's going to happen is you're going to randomize the action that you take, and then that implicitly will be randomizing over all policies which choose the same action. Okay, so that's kind of the key insight here. If you have a small number of actions and a large number of policies, a policy is something which maps the features to an action. You have a large number of policies, small number of actions. If you randomly choose an action, you're implicitly randomly exploring every policy which chooses that action. And that allows you to have an enormous improvement in the number of samples required compared to some strategy where you like try one policy and then try another policy and then try another policy and then try another policy. Right? You can have an exponential improvement, in fact, and I mean that with confidence intervals. All right, so you can randomize the action that implicitly randomizes the policy, and now there's kind of a key question, which is, can you actually use this data to evaluate policies which are kind of implicitly explored by the choice of action? And the claim is that yes, you can do this. So our experience is this XAPR quad. We have a large number of these quads. Our policy is something which maps feature to action. We want to know how good is the policy pi. The simplest way, this is not necessarily the best way, but the simplest way to evaluate this is you take an empirical expectation over your quads and you say, okay, big reward is good. Policy agreeing with a randomly chosen action is good. So this is an indicator function which is 1 when the policy agrees with the chosen action and it's 0 otherwise. And then we're dividing by the probability, which I think is the least intuitive part of this formula. But it turns out that's absolutely necessary. Yeah? Probability of the action. So you at the moment when you are going to choose an action, this is something which the platform helps you do. At the moment when you're going to choose the action, you have a distribution over actions that is generated by the model or system or whatever that you're using. And then you draw from that distribution over actions, and then you record the probability of the action that you chose. No, pi is any policy. So anything which maps features to action. So you have to understand that there's two policies running around. One policy implicitly is a policy gathering the data. The other one is the policy that we're evaluating here. Pi is the policy that we're evaluating here. The policy that gathered the data is implicit. All that we have is this information from it. We know that the policy gathering the data chose action A with probability P given features X. Yeah. Are there other questions right now? Okay. Okay, so claim is that for every policy that you might want to evaluate, for any distribution producing features and a hidden reward vector, the expectation of that value is equal to the expected reward of the policy's chosen action. Okay, so this is what you would expect, or this is what you would hope for. And the proof is something very simple that people don't believe until you actually see it once. So I'm going to show it to you once. So in general, you can worry about the expectation over the random draw of X and R, but you can just fix that for the proof. And then the only randomization that remains is the randomization over the action. And then we can say, oh yes, randomization over the action is really the sum over the actions, or the probability of the action times the thing inside. And now you can see why the p's are going to cancel. So that's why you wanted the probability of the action in the denominator. And the indicator function is going to cancel with the sum, and you're just going to get the expected reward of the policy's chosen action. So this holds point-wise for every individual sample. And so it holds an expectation over all the samples, and so you're golden. Right? Okay, so I've actually been involved in many projects trying to use these kinds of techniques in practice at various companies, and things go wrong. One problem thing that goes wrong is different parts are different people. So I remember when I first went to, before I was at Microsoft, I was at Yahoo Research, and I was in the hot jobs office, and I went and said, okay, maybe we should help optimize the search engine. And so I went and talked to the guy who's in charge of logging, and he's like, so I said, hey, do you log the results that you return to the recruiters that are going through the hot jobs office? This is one of these sell access to resume type of startups. And he said, oh, yes. And I was like, okay, do you log what they click on? They said, oh, yes. All right, then let's just join it together. He's like, oh, no, you can't do that. Because he didn't log any way to join. There was no way in the logs to actually join the outcome to the event itself. And it wasn't his job to do this, so he didn't care, and so nothing ever happened. Right? So wrong logging is a fatal error here, which happens very often. And there's a lot of ways you can see failures. So one which is the most nasty failures is when if somebody randomizes, or at least they say they randomized, but they don't actually randomize the way that they said they did, or maybe they didn't understand that you meant conditional probability rather than marginal probability. And then, yeah, it's just terribly difficult to debug something like that. Sometimes there's logging of the outcome. So maybe you're making an intervention in a stream of operations, and maybe the final outcome is logged, but you don't know what your intervention was. And then you have a problem because you don't even know what your true action was, the one that you can actually control. So there's no way that you can learn to control in an effective fashion. Okay, so this is the rough design of the system that we have at a high level. So there's a client library or web API that you can talk to and say, oh, here's some features, and it says, oh, take this action. And then later on, you can tell it a reward. This system outputs quads when there's an event. So it's the features, the action, the probability of the action, and then you have a key, which is a join key, to prevent that bug that the hot jobs guy exhibited. And then, of course, you can later on report a reward or some outcome with the key, and there's a join server that will join this. And the way to think about it is every individual event is its own experiment with its own experimental duration, during which time we join the outcome. And then the join server outputs essentially a cooked log of here's the features, the action, the probability, and the reward. And that goes into a learning algorithm. So it's just going to go through things, explore, join, learn, and then you want to deploy. Okay, so now this sounds kind of nice. It's kind of the sensible and obvious thing that you would sort of want. The thing which is kind of surprising is that this has really not been very standardized as a technology, but I believe it will become standardized as technology because it's just way better than the old approach of, hope that causation is correlation and run with it. Okay, you can also do offline learning. You can train your different model parameters. You can use different features. You can use different exploration algorithms, and you can get estimates of how much people will be setting, or how much people will click on your news article or whatever. And those estimates are actually reasonable. They're what would have happened in a counterfactual sense if you had used that policy at the time that you were deploying, at the time that you were gathering the data. Right, so it's not quite saying what will happen in the future. It's saying what would have happened in the past. But it's a much stronger answer than area under the precision recall curve. Okay, so this is all open source. I'm proud of that. I would like to take credit for Microsoft becoming more friendly to open source, because when I first went to Microsoft about 4.5 years ago, I forced them to sign an agreement that I could continue working on VW as an open source platform. But the truth is, the larger trends, I think, are really why Microsoft has become much more friendly to open source. Yeah, so it's way better than any kind of check a policy. Okay, that didn't work. Check another policy. That didn't work. Check another policy. Oh yeah, that worked. Keep that one. Now check another policy. This kind of approach is just horribly inefficient compared to what you can do with direct learning of causality. This is actually deployed. It's deployed on MSN. People use it for optimization. So they call this part here the info pane. It sees a lot of use there. They also call this part over here the river. It sees a lot of use there. It's deployed in many different markets. It's eating lots of traffic. People are very happy with it, et cetera, et cetera. So there's lots of users. The models are getting updated. There's lots of features in the system, and it made a big difference in terms of how engaged people were. The goal here was finding news content people would actually want, not revenue, but of course, one leads to another. All right, so that's great. And this is a story that I think many people could have told, but now it's actually deployable. Now, I want to skip to the end here. So if you go to this URL, you can actually, there's a button there that's deploy to Azure. So you need a point to aggregate the information. So you need some sort of cloud or computer or something. So you can go to this website. You can instantiate your own version of a Contextual Bandit service, of the decision service, in your own account. And then you can start sending it features, getting back actions, sending back rewards, and it will start adjusting to what you want. Right? And I think there's a potential that this will actually lead to machine learning which is easier than even normal supervised machine learning, because it's just an interface. And the details that people get wrong unless they take data science classes are typically gone from the system. All right, so yeah, there's a paper discussing the architecture of this in detail, and the core algorithms are in VW, which you can start there. Are there questions?